Okay, let's start. Hello, everyone. Welcome to the poster session of the ngEHT 2022 summer meeting in Granada. So in this session, we have 6 lightning talks for the posters that are over there. So each of them will have around 2 minutes lightning talks, and then we can move to the lobby next to the auditorium for discussions. So first we have Abhishek, Joshi. So please, your. I'm kidding. Okay. Yeah. And which?
Well, I can get started with my introduction. Yeah, hey everyone, I'm Abhishek. I'm a third-year graduate student at the University of Illinois, and my poster is about work I've done on circular polarization. This is in collaboration with Ben Prather and Charles Gammy from the University of Illinois as well. And so just really quickly, I'll give you the outline of what the project was. Basically, the paper 5 of both SAGE and M87 had these large libraries of thermal models. And we looked into these libraries to see what the circular polarization was, in particular, what the image integrated circular polarization was. And so what I just want people to take away from this confusing plot is just a large amount of models that we looked through to characterize the integrated circular polarization fraction, which means integrated over the image. And so these are just, half of the models. These are just the MAD models for SAGE. And so we have the same models for SAGE and for M87 as well. And we tried to characterize the distribution and just to see what sort of parameter dependence we had across, spins, R highs, and inclination. And we also included the effect of field reversal, which was mentioned in the M87 Stokes V project. Circular polarization, the distribution of it at least changes a lot when you change the sign of the magnetic field. And so we re-imaged our libraries with a flip in the magnetic field and tried to see what happened. And the results were complicated. I can talk more about it outside. And at the end of the day, we tried to see what observations of zero baseline circular polarization fraction told us about our models. As a test, we used the ALMA polarimetric light curve data from Bauer et al. 2018. And we tried to see if there are any trends in the constraints. Papers in the past have suggested that circular polarization, albeit at lower wavelengths, can constrain the sense of rotation of the source. But this could also be true for 230 gigahertz, since the sign of circular polarization that has been observed has been approximately the same for almost a decade now. So come talk to me outside if you have more questions about whether this was constrained or not, and sort of how circular polarization behaves and with respect to the parameter space. Thank you.
Okay, thanks, Abhishek. Next, we have Roman Burridge. Please, 2 minutes.
I'm Roman Burridge, and I'm going to be talking today about water megamasers. So water megamasers are able to they are an excellent measurement of mass, distance, and inclination angle. NGC 4258 is the best example of this. VLBI previous measurements have previously implied that this source would not be able to be imaged by VLBI. However, this red dot right here is a recent image of this source, and it implies that it in fact can be imaged by VLBI. This line is an inverted spectra model, and the red dot, which is the image that has been imaged for NGC 4258, lies on this line, implying that it may be a ADAF system, and in the future, we want to conduct a multi-frequency, multi-megamaser survey, and these are the sources which we are looking at. One final note is that it has been shown in 1998 by Herrnstein that this image, or that this signal is not coming from the center of mass or black hole, because they did a convolution of the northern jet with the beam and had no emission from the source or from the center of mass. And this was done at 22 gigahertz. Thank you.
Thanks, Roman. Okay. Next, we have Micaela. So please.
Hello, my name is Micaela, and I just completed my master's at the University of Pretoria. I'm just reporting on that work. As we all know, and we've heard many times over the last 2 days, there's a large library of GRMHD black hole models that are varied and need a lot of exploration. So in this work, I applied an unsupervised learning algorithm, specifically a self-organizing map, to generate representative prototypes of 10 to the 5 black hole models that varied in black hole mass, R high, spin, inclination, position angle, and they were generated in a sane environment. The self-organizing map that we used had a rotation and flip invariant similarity measure. It's kind of analogous to a distance measure, which means that if there are any geometrical differences between two images, it kind of becomes nulled because it will be flipped and then, yeah. So this is the self-organizing map, the prototypes that were generated from the algorithm. As we can see, there's a lot of lost structure in the ring, and there's only really a pattern between large rings here and smaller rings here, but no other morphological differences or clusters can really be identified. After we generated this map, we mapped all of the images, model images, to the nodes, so they were clustered based on their similarity to each prototype, and then we plotted the parameter distributions per node. And on the x-axis here, we have the full range of the parameter, and the y-axis is the normal frequency. As you can see, the black hole mass is well constrained. R high, not so much. There are some that are quite narrow in their distribution. A star was quite all over the place. Sometimes you'd have models almost equally on either side of the range. And I just included the inclination here just to show that it's very noisy because of this type of similarity measure. I think it would be very useful if we could repeat this sort of process with more constrained parameters, since we know more about Jimenez star and Sergio star. And it could be useful in identifying a meaningful subset of models that can be used for further, more complex analysis, rather than using, say, 10 to the 5. Yeah. Thanks.
Okay, thanks, Micaela. Okay, next poster is by Kiana, Salehi.
Hi, I'm Kiana. I'm working with Avery Broderick. And all right, we all know that black holes are characterized by their mass and spin. And we call this no-Earth theorem, but we can actually observe some deviations from this theory. And I try to describe it by starting from a spherical asymmetric stationary metric like this, which is a general case. It's not necessarily some perturbation to short shift case. And we all know that we can put some constraint on n prime, which is like the yellow shaded region here, by measuring the shadow size of the black hole. But what I've done was trying to looking at the multiple photon ring. And we all know that the photon ring actually composes of like different photons coming from different impact parameters. Like for instance, this one coming from this impact parameter from infinity, circulate 1/2 around the black hole, and then goes again to infinity, and we can detect it here. There's another photon coming from different impact parameter, circulate 2/2 around the black hole, and then again, will continue its way to infinity, and then we can again detect it here, and so on. So we can actually characterize this photon, subsequent photons by the number of times that they circulate half-time around the black hole. And what I've showed, what we know is that like we have another observable quantity, which is the relative distance between the radius of the subsequent photons. And it's proportional to this gamma, which is the Lyapunov component. And what I've shown was that this Lyapunov component is actually a function of n double prime over b squared and n prime. And as you can see it here, for different n prime, we can have different lines for n double prime over b squared. And we can put some constraint on GRR component of the metric. So we can come up to me and be like, hey, Kiana, I have a modified gravity, and I can put some constraint on it. Thank you.
Okay, thanks, Kiana. The next poster is by Alejandra.
Thank you.
Hi, everybody. I'll keep it short and sweet. My name is Alejandra Jimenez Rosales. I'm a postdoc at Radboud University. And the project that I'm presenting is using image moment invariance to characterize black hole accretion. So we use numerical simulations with this setup over here where we have a splitting black hole, and then around it we have the matter around it. We calculate images with it. Scalar images that we use are total intensity, linear polarized flux, and circular polarization. And then we calculate this image invariance, which are given by some complicated polynomial that you can find in the poster, and look at their variability in time for these different types of simulations. And so what we also do is we look at vector field invariants, which apply to this case are using the polarization vectors. We also look at the variations. We find that ngEHT and sane exhibit different ranges of variability over there. And yeah, if you have more questions, you can drop me an email or you can just talk to me and I'll be somewhere around here. That's it. Thank you.
Okay, thanks, Alejandra. So we have one more poster, which is not in the schedule, but the poster has been there for several days by Iris. So please.
Yeah, it's okay. So hello everyone. I hope you can see something because apparently the resolution didn't scale super great. But my name is Jimenez. I'm a PhD student at Radboud University. And this is my first work on trying to estimate model parameters from GRMHD simulations using Bayesian statistics. So we start with the ground truth, with the GRMHD model. We perform ray tracing and using some random physical parameters. And then we feed this ground truth to Themis and we let it rerun many times its own, it calls IPOL and it runs many ray tracing. And then it tries to combine the values that it finds from the synthetic data from the IPOL trans with the ground truth, and slowly it converges to the truth. So the first thing we tried was kind of the simplest parameter fitting with two parameters together. One of them was always PA, and then it was M unit, inclination, and R high. And you cannot see it, but actually all of the simulations converge very well to the truth. Then we tried to do this with all parameters together, and that worked also very nicely. Indicatively, this gives an chi-effective square of around 10 for this fit. And then the main or the more interesting thing that we tried is this generality of the pipeline. We changed the model to see that this can work for other models as well. And this is the blue fit here. And again, all chains converge exactly to the truth, which was very nice. And then what we did is we gave Themis the GRMHD simulation of 100M later, a time step 100M later, and then we let it and to try fit the previous time step with that, so it didn't have an access to the actual truth. And this is the green fit here, and even though it misses the truth by 10 to 30% in all parameters, it still comes close, and we think that by twitching the error bars, inflating the error bars in the fitting or in the truth, we can give it the freedom to converge to the truth even further. So in conclusion, we believe that this is a great step towards Bayesian inference of GRMHD models. And thank you very much for your attention.
Okay, thanks. Let's thank all the speakers again. So, yeah, if you have any questions on any of the posters, I think we can now move to the lobby and have the discussion right next to the posters. Okay, yeah, thanks for participating and see you tomorrow.